here we talk about the resistance and resistivity. So I think it is just a simple concept because yeah, I suppose you should have learned it in high school, physics. So so it's just about if we apply the same potential difference between the end of a geometric similar rod of copper and of glass, and very different current results, because as you know, this is copper is conductor and the glass is isolator, and yeah, we use the resistance to model the resistivity, something like that. Yeah, the ability to conduction. So the characteristic of the conductor that enter here is the resistance. So I suppose you should have learned this so-called the Ohm's law, V equals IR. V equals IR is so-called the Ohm's law. Ohm's law. Okay. So here it's written like R equals V over I, which means if we have a resistor, then we apply a voltage difference across it, then the current will follow this equation, like R equals VI. And yeah, so given a resistor, if we try to increase the potential difference across it, and the current will increase proportionally, then it remains the same resistance. Okay, so V is the potential difference across the conductor, and I is the current going through the conductor. So it's nothing special. Okay, so this is another one. So I think last time I mentioned something incorrect. So this is not actually the full version of the Ohm's law. It should be the latter one. This one is not the but yeah, at least this formula is important. I think this one should be the vector version of the Ohm's law, the vector form of the Ohm's law. So here it says we also define the resistivity. For the previous page, we talk about the resistance. The resistance depends not only on the material itself, but also depends on the geometric shape, like the length or the cross-section area. Maybe next page we will talk about it. And here we also introduce another variable called the resistivity. This resistivity only depends on the material itself. So here the rho equals E over J, or in the vector form we write it as E equals rho times J. So this is the E field inside the material, and this is the current density. So yeah, as you know, the E is related to the potential difference. Like if we have uniform E field, so it will be like E equals V over L. The L is the length of the. So suppose this is a resistor, and this is the length L. So if we have a voltage difference V here, then there will be E field going to the right side. So E equals V over L, and also J, the current density is I over A. A is the cross-section area. So J equals IA, and then if we just substitute this one into here, so we will get V over L equals rho, and then times I over A. And if we just move this one to the right side and then group this term together, it will be somehow like V equals I times R. R will be this one times this one over this one. So we have something like V equals IR. So we call it the recta form of the Ohm's law. And yeah, he also introduced another variable called the conductivity, which is just the reciprocal of the resistance. Yeah, later on we seldom use it, so just an introduction to it. Okay, so here we talk about the resistance of a cylindrical resistor. Yeah, we will not talk about other shape of the resistor, so only this type. So for the resistance R of a conductor, wire of length L and uniform cross section. So the resistance will be like R equals rho L over A, just as what we shown here. So if we slightly rearrange this, we will get V equals rho L over A times I. So comparing with V equals IR, then this one will be R. So we get this expression. So A is the cross-section area of the resistance of the resistor. And here it also talk about the resistivity is related to the temperature. If so it follows this equation, although we will not use it later, but it's just introduce this one. So I suppose you have learned the analytic geometry. So it's like a straight line. So we can regard this is somehow like y-axis. This is the x-axis. So the temperature in Kelvin in the x-axis, and rho is in y-axis, which is the resistivity. So which is like so in I think in analytic geometry, you should have learned something like y minus or y0 equals m times x minus x0. So x0 is the x-intercept and y is the y-intercept, and m is the slope of the straight line. Okay, so it's like this. So actually the physician try to measure the resistivity for different temperature, and then it looks like a straight line, and then they try to extrapolate this line up to the 0 Kelvin. So or maybe this is just a T0. Maybe the room temperature. Yeah, actually this is the room temperature. And then this is the rho 0 is the resistivity at room temperature, and then it try to extrapolate it with a alpha times rho 0 is the slope of this line, and then it can just go to the 0 Kelvin. But actually some interesting phenomenon will occur here, which is about the superconductor. We may mention it later. Okay, so this is just a minor point. We just go to this part. So this is a table summarize some of the resistivity for different materials. So for this part is the conductor. So as you can see here, the resistivity mainly use the gold, the copper, and the silver. Mainly use these several ones. So usually for the wire in the home, so we generally use copper because it is less expensive than the silver and of course the gold. So even though the resistivity of the copper is higher than the silver, and for the gold the resistivity is even higher, but it is more stable. It has less chance to have a oxidation reaction. So yeah, the gold is more stable, but of course it is very expensive. Okay, so here we can see some of the semiconductor, yeah, which this time you may not be so familiar with it. And of course we can just check here. So here it talk about the pure silicon. For pure silicon, the resistivity is very high, which means the conductivity is weak for the pure silicon. Because if you have learned the chemistry, high school chemistry, you know silicon is in the fourth column. Carbon, silicon. So there are 4 electrons for the outside of the outmost electron shell. So for pure silicon, similar to the carbon, it will form something like the single covalent bond, so that there are few of free electrons to move. So the resistivity of the pure silicon is high, but for our chip design, we will try to make it as N-type semiconductor or P-type semiconductor. So sometimes you may heard of something called a CMOS. If you are familiar with the computer, maybe you just enter the BIOS, something like that. You may have read this term called the CMOS, the complementary metal oxide semiconductor, which include the NMOS and PMOS, which is some kind of N-type metal oxide semiconductor and P-type metal oxide semiconductor. So to get this, we can try to have some pure silicon, and then we try to make it some 5A element. We get some 5 element into the pure silicon, so-called depletion. We try to make some 5A element into the silicon, so that there will be additional electron as the free electron to improve its conductivity, so that you can see the resistivity for the N-type semiconductor is around 10 to the 7th power smaller than the pure silicon. And for P-type semiconductor, we can add some 3A element into the silicon, so that for the outmost sphere, then there will be 1 less electron, something like that. Because if you have for a single silicon atom, it has 4 electrons at the outmost sphere, but as much as it forms 4 of the covalent bond, there will be approximately 8 electrons for each nucleus. So it will be stable and less free electron to move. But here, if we have some 5A element going in there, just say if we have P with 5 electron, then there will be some electron are free to move. Similarly, if we have something like I don't really forget what is maybe N. I'm not sure. B with only 3 electrons, then there may be 1 less electron for the outermost sphere, so that there may be some electron to move into this gap, and then it forms some kind of current. So here for the p-type semiconductor, it is also it has a much less resistivity than the pure silicon, but also, although it is slightly larger than the n-type semiconductor. But yeah, it is useful, Okay, although the resistivity here is much larger than the conductor, but for the semiconductor, it has something called the Laninet Effect, so that it makes it more useful to build a chip, because for the material it is linear, so it is not difficult to reconfigure it to do computation. But for the semiconductor, it has some nonlinearity effect, so we can really make it to build some complicated operation, like building the computer or whatever circuits. Okay, so this is the insulator, so it has a much larger resistivity. Okay, so here is a sample problem. So here it says a rectangular ball of iron has dimension 1.2 times 1.2 times 15 centimeters. A potential difference is to apply to the block between parallel sides in such a way those sides are equal potential surface. What is the resistance of the block if the 2 parallel sides are the square end? So let us do the first question. Okay, so for this case it is like this, 1.2, and then this is 15 centimeter. Okay, so we pick this to be at one end, this one to be another end. So the cross section is like this one. This is the cross section. Okay, so A is 1.2 centimeters. Okay, like this. So this is 1.44 times 10 to minus 4 meters squared. So in this case, R equals rho L over A. So rho according to the table, we have 9.86 times 10 to the minus 8th power, and then times the length. The length is 15 centimeter, 0.15 over 1.44 times 10 to minus 4th power. So this number is 100 mil ohm, micro ohm. Okay, so for the second one, it says 2 rectangular sides with dimension 1.2 times 15. So here it uses like this. So this is 1.2. This is 15. Now we use it like this. This one. So the cross section area is this side. Okay, so in this case, A is 0.012 times 0.15, which is 1.8 times 10 to minus 3rd power, and then a meter squared. So now you can expect a much larger cross-section area and a shorter length for the resistance. So now the resistance should be smaller than this one. Okay, so here R equals rho L over A. So rho is also 9.86 times 10 to minus 8. and then the length is 0.012 all over 1.8 times 10 to minus third power. So this one is a 0.65 mu ohm. Yeah. Okay. So even the actually the same resistance, but if you use it like this side and this side, and for this case, this side and this side, the resistance can be much different. Okay, I think it is simple. So here is talk about the Ohm's law. So I don't think it will be difficult. So yeah, so we just need to remember the Ohm's law is like V equals IR is enough. So this is a resistor, and then the current going through is I, and then the V is the potential difference across this resistance. That's enough. Yeah, actually, this Ohm's law is for some of the electrical device, but for some other device, it might not be something like this. This is so-called linear. So it's just like a straight line for this is the current, this is the voltage. The current versus voltage is a straight line, but some other element, it is not like that. Yeah. Here it says for figure C, this one is a plot of for another conducting device. Current can exist in this device only when the polarity of V is positive, and the applied potential difference is more than about 1.5. So this is 1.5. When the current does exist, the relationship between IV is not linear. It depends on the value applied potential difference V. So do you know what is this device? Anyone of you know this? Okay. Okay. Actually, this is so-called a diode. In Chinese, it is called 二极体. So for the electrical symbol, it is like this. So if you apply a voltage, for example, this one is V, this one is 0. V is a positive value. Then there will be no current going through it. So there will be it will somehow like open. But if you have a forward voltage, this is 0, then there will be current going through it, and the current will be exponentially decrease, not linearly increase. Okay, so Ohm's law, yeah, don't think, we just skip through it. Okay. So here we talk about the Ohm's law with a microscopic wheel. So yeah, for this one, you may consider for the physician they try to they have a resistor there, and then they try to have adjustable battery, which means that you can adjust the voltage difference across the battery, and then the physician try to measure many different points. For example, if there are no voltage difference, it measures this point, and then if he try to increase the voltage difference, here it measure of current, and then for this point, so on and so forth. Okay, and then after he measure many points, he can see that it is possibly be a straight line, so it try to connect them together. So this line may predict other variables on this figure. So it's somehow like the regression. Or you can call it curve fitting, which we usually use it for the somehow it's called the AI. We try to use this model to predict the future. For example, if we have increased the voltage up to here, then you may expect the point should be somewhere there. So this kind of analysis does not related to the physics itself. It is related to mathematics. So this is one approach to get this law. So the physician should try to consider whether this law is reasonable from a hardcore physics point of view. So they try to derive this to verify the Ohm's law getting from this way is reasonable. So that's the point to mention this part. Although even though you use this for calculation, it might not be so accurate. Yeah, but actually it can at least tell you this law is reasonable. Okay, so here it says the assumption that the conduction electron in a metal are free to move like molecules in a gas lead to an expression for the resistivity of a metal. So if the electron of the mass m is placed in an electric field of magnitude e, the electron will experience an acceleration according to the Newton's second law of motion. We have F equals ma, so we have A equals m over F, A equals F over m. And then according to the Coulomb's force, the force, as much as the electron is placed in the E field, the uniform E field, so F equals E times capital E. So we have A like this. And then it assumes the drift speed is like A times the tau. And it says tau is the average time between collisions. The argument here is like, for example, starting from the beginning, we assume an electron is at rest at the beginning, and then according to the E field, it will start to accelerate. So the speed of the electron will start from 0 to A tau, because A is the acceleration, and then times the average time between collision. So it starts to accelerate until the electron may collide with other nuclei. Then it will stop and then accelerate again. So this is an approximate drift velocity or the drift speed of the electron. So you may consider whether it should be 1/2 of it or whatever factor multiplied to this, but it doesn't really matter because it's just to verify the Ohm's law is reasonable. So it's just an approximation. So here we use Vd equals A times tau, and then we can just put this one, put this one, A equals E over m into here. So we have Vd equals E over m times tau. So we just eliminate A. And then according to the previous equation, we have a J equals Ne times Vd, And so we can plug this Vd into here. So we have Ne times E over m times tau, like this. This is the current density equal to this term. Okay, so we slightly rearrange the term. So we just keep E on the right side and we move over other terms to the left side. And then we just swap the left and right. So we have E equals M times J over E squared, and then N times tau, like this. So and according to the vector form of the Ohm's law just mentioned before, we have E equals rho. Rho is the resistivity, if I remember correctly. Here, yeah, rho is the resistivity. E equals rho J. E equals rho J. So comparing this equation and this one, we have E and then J here. So rho should be equal to the whole term here, like this. So we have rho equals M over E squared and tau. Okay, so here we can see that rho is the resistivity, and then and as mentioned, rho only related to the material itself. It does not related to the geometric shape. So here, according to this term, M is the mass of the electron, so it's a fixed value. E is the elementary charge. It should be also a constant. So these two terms is a constant, and then for the tau and then N. N is the charge density. N is the charge, electron density. Electron density, which should be only related to the material. So the material should, different material should have different N, but for the fixed material, the density should also be the same, and also the tau. So we consider the N tau only related to the material, not for the geometric shape, because if you increase it in the length or in the cross-section area, these two terms shouldn't change for the same material. So we consider the rho should match what we assumed before. And that's why the physician should derive it to verify the Ohm's law. So this is like the hardcore physics point of view, to show that according to some physics theory, then it tells you that the rho should be a constant for a fixed material. Okay, so so metal obeys Ohm's law because the mean free time tau is approximately independent of the magnitude E of any electric field applied to a metal. So this is the argument here. Okay. So here is another sample problem. So it says, what is the mean free time tau between the collision of the conduction electron in Cooper? So actually we just make use of the equation in the previous page. Tau equals M over N square, N times E square, and then rho. Okay, so in sample problem 2603, we have N to be this value, and then from the table 2161-1, we have a rho, and in appendix B we have the mass of an electron. So we can just plug in all the values. We have a mass to be 9.11 times 10 to minus 31, and then N is 8.49 times 10 to the 28th power, and then E is what we similar the elementary charge 1.6 times 10 to minus 19 quantity squared, and then times 1.69 times 10 to minus 8. Okay, so this number is 2.5 times 10 to minus 14 second, or you can write it as a 25 femtosecond. So which is a very short time, very short time. collide. You can just imagine, for example, your computer or your smartphone, the processing, the clock for the processing unit is like maybe 2.5 gigahertz. 2.5 gigahertz. So for the period of the clock, it is like 400 picosecond. 400 picosecond, and 1 picosecond is 1,000 femtosecond, which is like 4,000,000 femtosecond. So this is the period of the clock for your computer or smartphone. Yeah, maybe a bit larger than 2.5 gigahertz, but yeah. But you can see this is much smaller than that one. Okay, so it also asks the mean free time lambda of the conduction electron in the conductor is the average distance traveled by the electron between the collision. What is lambda for the conduction electron in the copper? Assuming that their effective speed v is 1.6 times 10 to the 6th power. So just some primary mathematics. So which is like lambda equals V effective times the tau, which is like S equals Vt, something like that. So V is 1.6 times 10 to the 6th meter per second, and then times 25 times 10 to minus 15. So this is 40 nanometer. 40 nanometer. Okay, 40 nanometer, or 40 times 10 to minus 9 meter, like this. Okay, so it says this is about 150 times the distance between the nearest neighbor atom in the Cooper lattice, which means if you have a Cooper, like this, the lattice. I don't really know what is the shape of the lattice, but it says the distance here, for example, we call it d. D should be multiplied by 150 to be around 40 nanometer. 40 nanometer. It says something like this. So thus, on average, each conduction electron passes many copper atoms before finally hitting one. So it says, on average, the electron can go for 40 nanometer before for a collision, which means that an electron could go through 150 copper atom for an electron on average. Something like that. So it somehow verified that the atom should be somehow like the nuclear, and then many space should be empty. Otherwise the electron should hit the electron the nuclear frequently, but here it can go through 150 on average. Okay, so here we talk about the power. The power is simple, which is something like P equals IV, or P equals I square R, should be I square R, or P equals V square over R. So three of them are okay, because as much as we have V equals IR, we can just eliminate one of them. For example, if we have V equals IR, and then plugging into here, so we have I square R here. Or if we plug in I equals V over R, then we have V square over R equals P, like this. So this is the power consumed by the resistor. Or also you can also calculate the power, by a supply or by a battery, in this textbook, it usually draw the battery like this, but in the circuit theory, I used to drawing the voltage supply or the battery like this. Okay, so actually you can also calculate the power supplied by the battery using I times V to calculate the power supplied by the battery. So V is the potential difference across the battery, and the I is the current going through it. For this simple case, it is trivial because you can see for this node it is V, this is ground. So the voltage across this battery is V, this is V, and then the current going through it is I and I here. So the power consumed by this resistor is V times I, and the power supplied by this battery is V times I, which is actually the same number. So okay. So here we will briefly talk about the semiconductor and superconductor. Yeah, actually we will not see it anymore, but just some introduction. So the semiconductor are material with usually the silicon or germanium, something like that. Just the middle part of the periodic table. Yeah. But as I mentioned, if it is a pure silicon, then the conductivity, the resistivity will be very, very high. And we need something called the doping. The doping. In Chinese is called 衬杂. To add some 5A or 3A element into the pure silicon to make it more conductive. Okay. So yeah. So after adding some 5A or 3A element, then there will be more charge carrier available, decrease the resistivity. Okay, so superconductor is another interesting phenomenon. Yeah, because at that time the physicians tried to measure the temperature coefficient, just like what we see before. Just like at that time we have a graph like this, and then if you still remember, the equation is something like this: rho 0 alpha t minus t0, something like that. If you still remember. So at that time, the physician also or the scientists find the liquid helium, so that it can achieve a very, very low temperature, close to the 0 Kelvin. And they try to further go to low temperature, but as much as they go to around 4 Kelvin, then the resistance suddenly drop to zero. So this is so-called perfect conductor without any resistivity. Yeah. So this is the so-called the superconductor effect, which needs a very, very low temperature to get this phenomenon. Of course, this phenomenon is very good, but not easy to achieve. It needs a very, very low temperature. So the scientists try to find some material which can still achieve this superconductor effect with a higher temperature. So most of the material require very low temperature, but some becomes superconducting at temperature as high as room temperature. Okay, so we have talked about most of the theory about the resistor, so we have some additional example. So this is the first one. So here it says the figure shows a person. So the story of this question is interesting. So here it shows a person and a cow, and then yeah. So here the capital D is 60 meter, and then it says a lightning of current I strike the ground at this point. The current spread through the ground uniformly over the hemisphere, 半球, hemisphere, 半球, center on the strike point. The person's feet are separated by radial distance. So this guy, this victim, separate his feet with distance by radial distance delta R 0.5 meter. The cloud here, delta R cloud is 1.5 meter. Yeah. So the resistivity of the ground roll is this number. The resistance both across the person between left and right feet and across the cow between front and rear hoof is R, 4 kilo ohm. We assume this path is 4 kilo ohm, and also this path. So here, what is the current I per through the person? Yeah. Okay, so here first we can calculate E equals rho J, rho ground. Okay, rho ground, the ground, and then equals rho ground. And then we assume the current density is uniform over the hemisphere. So we have I over the cross section. So for the full sphere, the surface area is 4 pi r squared, but here we only have the hemisphere. So we only have 2 pi r squared here. Now we consider the voltage difference or the potential difference across the person. So we have a delta R, delta V equals negative E dR, and then D plus from D to D plus delta R, D plus delta R. So for the person, this delta R is delta R per, and for the cloud, it should be delta R cloud. So I just make it delta R for this moment. Okay, so this is the equation in chapter 24. Then we can just plug in this one here because we get the expression of E. So it is like integration from D to D plus delta R. And then rho ground is a constant, and then I over 2 pi r squared dr. I. Okay, so rho ground and I over 2 pi are all constant, so we can just move it out. Rho ground I over 2 pi. And then the integration of 1 over r squared is negative 1 over r. So we have 1 over r, and then evaluate from d to d plus delta r. So it will be rho ground I over 2 pi, and then 1 over d minus 1 over d plus delta r. Okay, like this. Or we can further write it as d times d plus delta r, and then delta r equals rho ground I over 2 pi, like this. Okay, with a negative sign because should be reversed. should be like this, plus delta r minus 1 over d, because it should be this one minus this one. Yeah. So I person will be delta v, take the absolute value over the R, the resistance from here to here. Okay, so we can just plug in the value. Rho ground is 100. Rho ground is 100, and then times I is 100K. 100 times 10 to the third power over 2 pi, and then times delta R per is 0.5, and then here D is 60 meter, so we have a 60 plus 0.5 here, and then we still have this R is 4K. So we need to, maybe write it here, times 4 times 10 to the third power in the denominator. So this number is 0.0548. Okay, going from here to here, like this. Okay, so for the second one, we can simply apply the same equation, but we just replace our pearl by our cloud. So I cloud is 100 times 10 to the third power over 2 pi times here. Delta R cloud is 1.5, so this is a 60 plus 1.5 times 1 over 4 times 10 to the third power. So this number is 0.162A. So which is larger for the cow. Okay, like this. Roughly 3 times larger for the cow. Okay, and here we have a second one. So what is the current in the wire of a radius capital R in the magnitude of the current density given by this one, which R is the radial distance and J0 is this number. So this is just a practice for the integration. So here IA is integration of JA dA. So JA is this expression, so we just plug it here. So we have a J0 times R over R. And then we suppose this is a cylindrical wire. So we can use the polar coordinate for the cross section. So this dA will be nothing but R times dr d theta, for the polar coordinate. So we have R dr d theta. R is integrate from 0 to capital R, and then theta should be from 0 to 2 pi. So this one is like a J0 over R, is a constant, so we can just move it out, and then we have R squared dr, integrate from 0 to capital R, and then we have a d theta from 0 to 2 pi. So this one is 2 pi, this one is r cubed over 3. So the answer will be 2 pi j0 r squared over 3 over 3. So we can just plug in the value 2 pi times j0 is 5.5 times 10 to the 4th power, and then times r squared is this 3.4 times 10 to minus 3rd power squared, and then over 3. So this is 1.33a, 1.33a. J0, yeah. Okay, so this is the first expression, and then for the question B, the expression changed to this one. Okay, so it will be like IB equals JB dA, and then we can just plug in this one here, J0 times 1 minus R over capital R. And then dA is the same case, R dr d theta. We also integrate from 0 to capital R for dr, and then 0 to 2 pi for d theta. Okay, so we can just move out J0, and then we have R minus R squared over capital R dr from 0 to capital R. And then we have still d theta from 0 to 2 pi. So this one is still 2 pi. And for this one, the integration of R is R squared. So we have a capital R squared minus this one. This one, the integration of R squared is, R squared over 2. This one should be R cubed over 3 over capital R. So it will be R squared over 3. So this one becomes R squared over 6. So the answer will be 2 pi j0 R squared over 6 over 6. So which is pi j0 R squared over 3. And then we can just plug in all the numbers to find the answer to be 0.6678 for part B. So for part C, which function maximizes the current density near the wire surface? So it should be, of course, maximize the current density near the wire surface. Yeah, JA maximize the current density near the surface, because you can consider JAR is capital R. JAR should be J0. JA capital R is J0. But for JB capital R is J0 1 minus capital R over R, which is 0. Yeah, this is the point here. Okay, so before we have the break, we still have the last additional example. So yeah. So here it says the wire section 1 of a diameter D1 equals 4R, and wire section 2 with 2R. Connected by the taper section. Taper section is the middle part. So the wire is Cooper and carrier current, assuming that the current is uniform distributed across any cross-section area through the wire width. The electric potential change V along the length L, this part, is 10 microvolt. So the number of charge carrier per unit volume is this number. What is the drift speed of the conduction electron in section 1? So here we have E2 equals V over L, because we assume everything is uniform. We assume the charge density, current density is uniform. So the E field is also uniform. So in this case, this is 10 times 10 to the minus 6 power over L is 2 meter. These two number 2. So we have 5 millivolts per meter. Okay. So next, J2, which is the current density at this part, will be E2 over rho. So we have 5 times 10 to minus 6 over 1.69, which is this number, times 10 to the minus 8 power. So this number is 296 A per meter square. So we know the current density for the section 2, and as much as we will assume that the current at this part and current at this part should be the same, which means that the J1 times A1 should be the same as J2 times A2, because the current here is J1 times A1. The current here is J2 times A2, and they should be the same. So we have this expression. So we can be able to find J1 equals A2 over A1 times J2. Now we can get this. So we have A2. A2 is the cross-section area here. So the diameter is half of it. So the cross-section area, you can expect it to be pi r square for this part, because the diameter is 2r. So the radius is r. So we have pi r square for this part. And for A1, the diameter is 4r. So the radius is 2r. So we have a 4 pi r square. And then times J2 is 296. So J1 is 74 A per meter square. And then finally, we can make use of VD equals J over NE to find the drift velocity will be 74 over 8.49 times 10 to the 28th power, and then this is 1.6 times 10 to minus 19. So this number is 5.44 times 10 to the minus 9 meter per second. Okay, so yeah. So I think that's the end of this chapter.